So here is the theorem. It's due to Nesterov on just first-order stationary points. Okay? So let's assume that we have a gradient Lipschitz function. So if you know some mathematics, you'll recognize that. The gradient doesn't change very much between points x1 and x2. A stationary point is not exactly that the gradient is equal to 0. That would be, you would only converge to that asymptotically. We put a little ball of size epsilon around it. And we ask how far do you hit, how long does it take to hit that ball? And then we would, for any epsilon. And that gives us a rate of convergence into the optimum. And that rate was established by Nesterov, who showed that it's 1 over epsilon squared. Okay, so that's a pretty good rate. It's not super fast, but it's pretty good. But the key here is that there's no dimension in that equation. Right? Dimension, it's independent of dimension. So that is the amazing fact about gradient descent. Okay, so let's move on to the main point of this talk. What about second-order stationary points? Okay, so we're going to be interested in saddle points in particular. We could be interested in local minima. So we're going to now look at a little bit more smoothness so we can prove a theorem. So we're going to have Hessian Lipschitz. And the second-order stationary point is just an obvious extension of the first-order one. The gradient, again, is expected to be not 0, but close to 0. And the minimum eigenvalue is not expected to be strictly or greater than or equal to 0, but we give ourselves a little fudge room to, again, get a rate. Okay, so we can see how fast we approach this value. So here's the algorithm we're going to analyze. We're just going to call it perturbed gradient descent. It's just gradient descent. That's equation 4. Right? But occasionally, we will add a little bit of random noise. And we will add it when the gradient is small. That's at the bottom of the page. And we will do it infrequently, once at every t steps where t is a parameter we can tell you how to set. All right? So we'll do this in this particular theorem uniformly from a ball. That's not necessary. We could analyze other things. This is done for simplicity. Okay, so this is not stochastic gradient exactly. Stochastic gradient has noise on every step. This is what we needed to be able to get a theorem. Okay? And the theorem is amazing, so I think even this algorithm is worth kind of thinking about and considering.